Right, so I'd like to thank the organisers for inviting me to come here and talk. Hopefully you'll all find it a little bit interesting. This is mainly going to be about what we do at Diamond Light Source and how we use Python there to do various different everyday things. So basically I'm going to talk a little bit about what Diamond Light Source is so that you've all got an idea of where I actually work and the problems that we have. A little bit about big data. So I was asked about, can I give a talk about big data? So I'm going to talk about the types of big data that we have. And then I'm going to do a little bit about Python for scientists and a bit about Python for developers, because I think you can treat them in two different ways. So first things first, Diamond Light Source is a particle accelerator in South Oxfordshire. It's about the size of Wembley Stadium, which is excellent because I can actually point at it. I normally can't do that for a talk. It's about the size of Wembley Stadium, and basically it's, I'll show you the video because it makes a lot more sense. We accelerate electrons to very near the speed of light, and we use them to generate really, really intense X-ray beams. So, let me move my mouse out of the way. So basically this is just the outside. There's two sorts of parts to it. There's the main synchrotron building, which is where the accelerator is, and in the other room, or the other building, is where everybody who sort of just generally works on it lives. We're on the ground floor because there isn't a basement for the computer programmers. If you pull the roof off, basically there's three main parts. There's a linear accelerator, a booster synchrotron, and a main storage ring. And the idea is that we have bunches of electrons, we put them in the linear accelerator and we accelerate them up to about 99.99% the speed of light. They then go into the booster synchrotron and are accelerated up to 3 GeV, which is 99.9999999% the speed of light. And then we put them into the storage ring where they generate really bright X-ray light for us. So here we go, there's a little bunch of particles, or electrons at the bottom. They go into the booster synchrotron, spin up, and then eventually they'll go out into the main storage ring, and then you'll see them start emitting light. Now, basically they emit light to every single one of these beamlines that are around the outside here. And as I say, the light that they emit is incredibly bright. It's about 1 million times brighter than the sun. It's about 1 billion times brighter than a hospital X-ray machine. Very, very intense light that we generate. And that's actually part of the problem. When you've got very intense light, you can use very short shutter speeds for doing exposures. Now this is our little bunch of electrons. And what we do to generate the light is we wiggle it from left to right through a magnetic field. So it's an array of magnets. And then it basically drops the photons off down into the beamline, and the electron beam goes around the corner. Remember that for later, because there's a part that I'm going to talk about where we're talking a little bit more about that. As I say, the synchrotrons there, we've got various beamlines around the outside. And effectively, each one of those beamlines gets X-ray light of some form or another, but can use them in completely different ways. So each one of these different experimental stations can do totally different things. So what do I do? Well, I'm part of the software or data analysis scientific software group. I provide data analysis for use during and after beam time for users. A lot of our users may not have any prior experience of how a synchrotron works. So we get a lot of people who are people like archaeologists, paleontologists, who come along and they just want to use the equipment as a way of looking at their sample. They don't want to know how to reconstruct the data or anything like this. So we try to give them really useful data that they can take home rather than the raw experimental data. There's about 30 beamlines with about 100 different techniques that are used. And we try and support that with, it's myself and about 12 other full-time people. So we're relatively stretched on how much we can actually provide to each of these groups. So why am I talking at a Python conference? Well, it's good to see where it all started. Before Diamond Light Source, which was about 2007, there was another synchrotron at Daresbury, and they started in about 2002 writing a piece of software called the GDA, which is written in Java. And basically the GDA is generic data acquisition, and it's basically there to run all of our beamlines so that we're all using the same piece of software on all of the beamlines for controlling the motors, doing scans, and doing all these kinds of things. In about 2004, it was really appreciated that actually a key thing that would be really useful is some way of scripting this so that the scientists, rather than the software developers, could actually really increase the ability of what the software could do. They could optimize things, they could write all kinds of different codes to improve the beamline, do scans, do all kinds of exciting data collections. And Python was picked as the language because it sat neatly on top of Java, allowed you to access all the Java objects behind the scenes, and it was relatively simple syntactically. People could get the hang of it. What this meant was that we ended up with much, much faster beamline setup times, and data collection speeds were increased, made it a lot easier for people to use the equipment. That leads us nicely on to, well, why am I talking about big data? Making the beamline easier to use means that people can collect more data. Also, we've got this kind of universal data problem. If you've bought a mobile phone recently, you may well have a 41 megapixel camera on it. That's just insanity. We're getting exactly the same problem with experimental detectors, in that they're just getting bigger and bigger and faster. And to give you an example, in 2007, when we had first users, our data, our collectors, our beamline systems were running about 10 megabytes per second, absolute max speed. 2009, we got some really cool kit from Switzerland, and that suddenly started running at about 60 megabytes per second. 2011, they managed to make that even faster, 150 megabytes per second. Okay, so we're now no longer able to deal with this with 1 gigabit networking. We have to go to 10 gig networking for these pieces of equipment. 2013, we've now got about 10 machines, or 10 systems which have 10 gig links, and we've got 600 megabytes per second data collection systems. These can run almost continuously onto disk. And in 2015, we're looking at a new detector that can do 6 gigabytes per second. It's absolute madness. And if you look at how this works, if you not plot a nice graph of this, it's doubling about every 7.5 months. So the problem is that a lot of our kit won't keep up with this, and also not only is the individual detectors doubling, but we're getting more beamlines that are using more of them. So we've got a real data problem. Here's a sort of a schematic. These are all the different beamlines at Diamond. As I say, they all do different stuff. Not all of them are as terrifying as that. But there are quite a few of them that are red, which are collecting, not necessarily routinely, but definitely in peak over 1 terabyte a day. At the end of January, I did an experiment on one of the beamlines, and I collected 6.8 terabytes of data in 3 days. Just as an example of how much we can collect. That's raw data. So there's these different categories of beamlines and different amounts of data that we're collecting. Obviously, to deal with this, we've got data storage. We've got a large amount of data storage. We spend a lot of money on it. It has to be relatively high speed. We've got several petabytes of spinning disks. We've got, I think, potentially 5 petabytes of tape store to back all this data up onto. Very important. But the key problem with this, and the reason why I bring it up here, is that when you start going to these high-performance systems, and you say, you ask the vendors, what can I do with this? And you say, oh, I'd like to put, a couple of 100,000 1 meg TIFFs onto it, please. They go, sorry, what? You're not running a database on this. This really doesn't work with small systems. And then you say, and I'd like to LS that directory. And they laugh at you. So actually, it made a really big mindset change. We had to completely change the way we're collecting data, and we had to move a lot more to HDF5 and single files that contain a lot more data. The problem with HDF5 is that it's not an ASCII file, and you can't read it straight away, which causes a lot of issues for analysis. I wanted to put this up because in the next sort of bits that I'm talking about, not all of the data I'm talking about is necessarily just big in terms of volume. I really like this because everybody talks about big data in different ways. There's 4 V's here. I think there's another couple of V's in other people's talks. But basically, it comes down to that the data can be big because of its volume, its variety, just lots of different types of data that you have to deal with, veracity, how likely it is to exist, be relevant, those kinds of things, and velocity, how quickly it comes in. So, really good slide, I really like this one. Blatantly stolen from IBM. But essentially, it really does detail that a lot of these things are not just, it's not just the sheer quantity of data that's a problem. So, I'm going to start off actually with the small data rate beamlines. So these are the green ones, the less than 100 gigabytes per day. And the problem with them is variety of data. The reason they're generally low amount of data is because they're doing really different experiments. Each experiment they do is generally different. Here is a quote, I haven't named them to keep them anonymous, from one of the principal beamline scientists on one of those beamlines. So I have all the data I've ever collected on a floppy disk and processed it by hand. That was in 2005. And it was completely accurate. Unfortunately, detectors, new improvements and stuff, he's collected about 1 terabyte so far this year. It's a completely different setup for him. You know, literally 10 years ago, he was able to do all of his processing in stuff like Excel. There was absolutely no issue with that at all. You pop a column of data, no issues whatsoever. Yeah, MATLAB, IDL, eGOPRO, these are all really good pieces of software, and they work really, really well if your problem can be contained on your laptop. But as soon as it starts getting bigger, these become more difficult to scale. and change the title here slightly because processing data isn't always entirely true. It's generally playing around with data, investigating what's going on. And the key issue here is scalability. It's very difficult to take things like MATLAB and at a reasonable price make them scale across a cluster. Unfortunately, we don't get academic licenses on MATLAB even though we're academic, so it costs us an absolute fortune for every license of MATLAB we have. Very, very inefficient to put on our cluster. So, talking of clusters, we've got a reasonable number of these. We have them locally so that we can process stuff real time. It's really important that we've got instant access to these clusters. They're not massive, they're not really, they're not top 500 supercomputer clusters, but they're reasonably big, and they're very much tailored for batch processing because that's what we do. We generally have a lot of data and we want to batch process it. Most of our stuff is embarrassingly parallel. Hence the GPU clusters, very good. Sorry, this slide was also stolen because I love the fact that people put the number of cores on the GPUs. Always makes it look really impressive. So, Python's the obvious answer. The users have already used it during their beam time because they've used Jython, so they know the syntactic problems. They know that they need to use spaces and not tabs or the other way around. It's free and easily distributable. We can put it across our whole cluster and there's no additional cost. And I'm not going to tell you what the other amazing reasons for using Python are because there's been an entire conference on it. But we want to give it to them in a way that they can understand and that they're used to. Because as I say, some of these guys have got very little experience. So the key way or the easiest way for us to do that was to extend our acquisition tools. Luckily, in about 2010, the GDA went into a new system in Java, or a new thing in Java called Eclipse. So it's now written in the Eclipse RCP framework. And it made it very easy. At about the same time, our team split from just data acquisition to data acquisition and scientific computing as a separate group. And at that point, it was very easy to create a spin-off product that basically took the bits of the analysis and the visualization from the GDA and provided it in a way that users could take home with them or use in a separate way. As I say, it also added a few things like reading and writing for different file formats, various other bits and pieces. The reason I bring it up here is because it's what we now use as our main sort of environment for developing Python. In terms of the bits that are really relevant for Python, we use PyDev really heavily, so we put a lot of effort, and we used a really great contractor, Jonah from Kichwa, to put a lot of information into, or a lot of additional features into PyDev scripting to make it more interactive. And I hear that there's some people who are doing some more work on making PyDev IPython stuff work even better, so it's really good that that's sort of starting to kick off. PyDev is really excellent, by the way. It's a very, very, really efficient IDE for generating stuff. We also have a lot of data exploring. HDF5 visualization is standard because, of course, that's what we're collecting all our data to, so we need to show that. And we've got various ways of tying our Python to that visualization, because I believe there was going to be a talk this morning about how there's no visualization packages for Python. So we've got another one here. The idea was we didn't really want to recreate matplotlib or anything like this, but we already had a full visualization system that was quite interactive, so you can do things like peak fitting and function fitting and stuff just in the GUI, and it was what our users were already used to using, so hence we didn't feel too bad replicating up a load of stuff. The plotting is one thing. Just to give you a few ideas of what of how PyDev works, and as I say, it's incorporated into our project. Interactive console, we've got real-time variable view, IPython interface, which is quite nice, so you can use a reasonable number of your magic functions. Integrated debugging, you can pop a breakpoint in places, even in the interactive console, and it will stop on that breakpoint and allow you to step through. All kinds of useful things. Syntax highlighting, scripting tools, loads and loads of really cool features. Well worth being aware of it, if nothing else, and it's a really, really very good set of tools. As I say, it's incorporated in our product in Dawn, but you can just get it on its own. It's very, very good. So in terms of the Python that we use at Diamond, just to give you an idea of libraries and stuff like this, so we use the Anaconda distribution now, very convenient for us to install. And we mainly use it for the classic stuff, NumPy, SciPy, H5Py. MPI for Pi we find really useful for our cluster. And also we've got a few other toolboxes in there that you may or may not have heard about. Astra's a kind of a wrapper onto the Astra toolbox for doing tomography work. We use the wrapper for FFTW, and we use CCTBX, which is a crystallography toolkit. I'll talk a little bit more about that later. But essentially what this means is that very, very relatively easily we've moved from these guys who want to play with their experimental data, rather than using MATLAB IDL and having issues with support and issues with portability, a lot of them are now starting to use Python. It makes life a lot easier for us to support. And what as a group we're trying to do is basically to give them access to modules to make life easier for them, but also apply things like repositories, training, because essentially if they can write software that's actually going to be sustainable, I will point out, do go and have a chat with the guys from the Software Sustainability Institute if you haven't already. So very, very useful information on how to basically make sure that your code can actually live longer than your existing project. But basically trying to keep those kinds of features in place is really important. So that's what we're providing to them. But essentially it means that they can go off and do all their data processing themselves. As a slight aside, and I apologise to people who went to EuroSciPy 2012, because I did talk about this a little bit then, but a little bit of an update on this. We do also use Python for other things. So with the machine, if you remember when we were wiggling those electrons left to right in the video at the beginning, it's one of the things that we do to generate these really bright light sources. And so rather than data processing, using Python for optimization is really important. Here's what one of those insertion devices looks like in reality. It's about 600 magnets on the top and the bottom, and they form a really nice array. The only problem is that the individual magnets can't be manufactured perfectly. I mean, there's about 200,000 pounds worth of magnets there. You can't make loads and loads of them and pick the best ones. So they're not always brilliant. So the perfect one obviously would be exactly in the direction, the magnetic field exactly in the direction that you've machined it to. And they're always off by a few percent. So it's a simple optimization problem. You just need to take those 800 magnets, pick 600 of them in the right order, and create a perfect magnet array from it. The only issue is that the range of the magnetic field is quite high, so it actually becomes a really, really very complicated problem, which you can use various different optimization techniques to address. One of the plus points was that we had some code in Fortran already. It was a little bit hard to use, it was a bit difficult to extend. The key thing with optimization problems, there's a really good talk on optimization yesterday, is objective functions and how long it takes you to calculate your problem. So we need to calculate the entire magnetic field for this system based on all of the different magnets, and then effectively model what an electron would do as it moves through it. So our original code was about 1,000 times slower than than Fortran code, because it was almost a direct port. We didn't use anything clever, it was a load of if loops. NumPy put all into the optimized arrays, and we were about 10 times slower. The thing that was interesting though was that by the time we'd done this in the code, the Python was so much cleaner and so much easier to see and understand than the Fortran. It was really obvious to notice that there was some caching that we could do that brought up the speed to basically the same as the Fortran. And in fact, by using some clever updating, we could get about 100 times faster. If you're at the presentation in EuroSciPy, this said 400 times faster. This is why you should never use your benchmarking tests to show slides on. When we actually did the real thing, it actually ended up being not quite as efficient as we were hoping. But even so, is a significant improvement in time. The other thing that we then did was basically used, instead of simulated annealing, which was what the old Fortran code used, we used a global optimizer called artificial immune systems. So that's just slightly below genetic algorithms. If you have no real clue about what your problem is, but know that crossover won't work very well, you use artificial immune systems. They're pretty good for that. It needs a lot more evaluations, but gives us a much better result. The key was, though, that instead of millions of iterations, we wanted to do hundreds of millions of, or thousands of millions of iterations. So we looked at a little bit of parallelization, very, very simple parallelization in this case. We just used threading and NumPy. NumPy releases the GIL for all of its operations, so you can just use the standard threading library to process across. Very, very easy use. We got almost a perfect scaling on our cluster. And then we used MPI for Pi to parallelize across multiple machines, meaning we could quite happily run this on 25 machines, about 200 CPUs, really get the speed that we wanted to make the whole process very, very quick. And the nice thing is that literally since January, the first sort with this new code has now been used, and it's now been built into a system, so we're kind of committed to this now, and it's working really nicely. So back to our sort of high data rate beamlines. We're now going to look at the things that are generating more than 1 terabyte a day. And this is really the domain, rather than of the scientists basically who are playing around with the data. This is really about data reduction and data processing. So the first thing we need to do is archive the data. And in fact, you would think this was quite a simple task. We need to communicate with a web server somewhere and tell it what the data is. We need to give it some information about metadata and stuff like this. But actually, we need to check to make sure that the file really exists. We need to check sizes. We need to collect information. And in fact, it turned out to be a reasonably complicated problem. So as an example of where we're using Python as a kind of a routine script here, basically this just collects all the information from various different files, does a bit of XML parsing, makes sure that file sizes match up and these kinds of things, talks to web services, does all sorts of things like this. It scales nicely onto the cluster, which is very, very useful. And we've basically archived pretty much all of our petabyte of archived data so far through this system. So it's relatively happy with dealing with the 200 million files or so that we've had to process. Basically, it's not really dealing with much of the data, but it's having to deal with the fact that we've got large amounts of data just sort of lying around. In terms of actually processing these things, the red beamlines at the top here are the MX village. That's macromolecular crystallography. These guys have got very, very fast detectors, and they do things like drug discovery and drug development. The way that we use Python in these situations is actually as more of a pipelining system. There's a lot of software available for doing all of these sort of internal steps, but a lot of the software is single core, not necessarily parallelized, written in Fortran, not particularly reliable, all kinds of these sorts of things that are a bit annoying to run it on a production system. So what we do is we've got two different pipelines. The first one, FastDP, which runs, it basically takes all of this data. So they can collect something like about 8 or 9 gigabytes of data in about a minute. It takes that data and then parallelizes it across most of our cluster, does all these various steps on different programs, and then combines all the data back together, makes the best estimates it can, uses some other programs to adjust things, but essentially at the end of the process it's taking all of this data, using Python to parallelize it across all these different machines, and it's taking us down to a single output file. The nice thing about macromolecular crystallography is that 8 terabytes goes in the top and about 100 meg comes out the bottom. Really nice for data reduction. At the same time as that's happening, that takes about 2 minutes. At the same time, we use a different program called Zia2. Behind the scenes, it's using all the same things to call the cluster, so it's really nice code reuse. But this is an expert system. What this tries to do is solve your problem as a human would and try and get you the best result possible. This result is the quick result. This one is the high quality result. This takes about 20-30 minutes. So it's not so important, but if you really notice that actually FastDP hasn't given you the result you want, you can then use the results afterwards. This is done completely automatically for the user. It's really important. The next step is experimental phasing, and this is taking that tens of megs of data and it's putting it through. Once again, we throw it out to pretty much the entire cluster. We're making use of the fact that we know that we don't know a lot about necessarily the system, but we know that it's got to have some stuff in it. If we basically make a matrix of all the things that can be in there and solve all of them and then pick the one with the least error, we're probably onto a good winner. And this can basically reduce the data down to a electron density map, which is what you want out at the end of this. This is an atomic resolution map of the protein or whatever you're interested in looking at. Thank you. As we go through that process, once again, this isn't so much the amount of data, because we've already reduced it quite heavily, but it's the speed, it's the velocity that we need to deal with. And the whole nice thing about this is that it takes about another 2 minutes. And this is one of the reasons why we've got such a big cluster sat next to all of the data, so that we can process these things so quickly. So from putting the sample on the beamline and pressing the go button, they can pretty much automatically have, within 5 minutes, an atomic representation of the structure that they're interested in. And that's really important for the users, a very, very useful feature. I've only talked about using Python as a kind of glue language for making things useful. We're starting to move on to using Python as a more actually for writing the software that we're doing. So DARS is a project that basically is looking at taking a lot of those blocks that I told you were single core, were not very reliable, and writing better software based on that. It's got 4 full-time developers. It's an EU grant basically that runs through. It's built on top of this CCTBX crystallographic toolkit, which they're extending and working very closely with. And it uses, basically, we're trying to do this optimization only when required. So everything is written in Python. When we know that everything's working correctly, you identify what's slow, and then they use the boost libraries to basically write the rest of it down in C so that you get the nice performance improvements. The reason they chose boost was because it's tied in quite heavily with the CCTBX library, and it works very nicely. So this is an example of where we're basically not only using Python for pipelining, but also for actually doing data processing. I mean, this will have to deal with and have to compete with Fortran code, C code, so it has to be reasonably high performance. And I think the way that it's working is that it's, it's close enough that it's not a problem. So finally, I'm going to talk about tomography data reconstruction. This is mainly volume and velocity. The problem with these guys is that they collect maybe 100 gigabytes per data set, and it gets reconstructed to about 100 gigabytes per data set as imaging data. So once again, we're in a very similar situation to MX. We've got some C code that uses CUDA to do the reconstructions, but it only runs on TIFFs, it only uses one GPU, it doesn't really correct for all the experimental artifacts properly. So we wrap it up in Python that enables us to split the data and use the whole cluster. It allows us to extract the corrected data from the HDF5 files using H5Py and rewrite them as TIFFs onto the local file system for this program to use. And it basically builds input files from the metadata so the user doesn't have to specify all of this information, because when we collect the data, we include enough information with that in the collected files. So this is very much, this runs quite heavily. As I say, it's running on large quantities of data, but it's only wrapping up what's going on. The next generation of tomography, unfortunately, these guys decided that it would be really nice to be able to process the data. So you've got a 100 gigabyte volume of data. They want to process it in one direction and then process it in the other direction, which means we've effectively got to transpose the matrix and do transfer between all the different nodes of our cluster. So essentially, to do that, we're looking at using MPI for Pi for the cluster organization and queuing and parallelism. But then using 0MQ and using BLOSC as the transfer mechanism to try and compress the data as we transfer it across. Currently, we're still going to be using the external codes, but the idea is to move them into Python as soon as possible, because there are some really good libraries in Python for doing reconstruction and those kinds of things. And a lot of them are basically making calls to the GPU. And to be honest, in terms of performance, it doesn't really matter if you're calling CUDA code from C or Python or Fortran. It's still calling CUDA code on the card, so it makes very little difference to the performance. Somebody brought up the concept, and there was a profiling talk yesterday, and I added these slides in very briefly. This was my answer to how to deal with profiling on multiprocessor and MPI systems. So basically, all I wanted to do was basically see how things were running in parallel. And the thing that I really noticed was using threading and multiprocessing was that because my H5Py process was holding onto the GIL, I couldn't get it to stop doing that. I got this very distinctive tick in all the rest of my processes whenever they actually got a couple of seconds to run various different things on the queuing system and all these kinds of things. So actually it was really useful having this kind of diagram that basically displayed, so these 4 threads are 4 threads that are running on one processor or one machine. These 4 are the next machine and the next machine. It's not quite as fine-grained as proper profiling. It's basically based on log messages, but at least it gives you an idea of what's going on. And when I looked at it with just the MPI, I got a much better alignment. I didn't have a lot of these blocking issues, so that's why we're choosing MPI now. As I say, I use these graph structures quite a lot now. And it suddenly hit me. I mean, this was very much, it was a case of using some JavaScript, so I talked yesterday as well. JavaScript, I just used the Google Visualization data table just as a way of displaying the data. I basically just set up my logging config with a few bits of information in there so that whenever I call a logging message from MPI, it just includes the machine number and it includes a rank for the machine, or you can include the thread name if you want to, depending on what mechanism you're using. And then I just use Ginger2 templating to basically to tie the two together to produce an output. It just takes my log file, converts it into an HTML file. I can just view that and see what's gone on with my process, because it's a damn sight easier than grepping out, okay, process 5, core 3. It's a real nightmare to grep that sort of information out and see what's going on, especially when you're trying to relate it to other things. Anyway, where are we going? So from my point of view, with the amount of data we're collecting, scientists have to become developers. The idea from our point of view is to try and steer them in the right direction so that they're doing a good job rather than just hacking code together. And at the end of the day, Python is a very good, if not the best tool for this. There's no other system out there that we've found that allows scientists to use or allow them to do as much as they can in Python that easily. And the next step is that developers are having to work faster and faster. There's 12 of us, we've got to support 100 different techniques. We've only got maybe a couple of days to sort out one of these techniques, so we have to be able to implement it very, very quickly. And Python really does allow that, and for anything that we're running on the cluster and any computational techniques, we generally look at driving them in Python. Python's our go-to language for doing most of these things. If it's graphical, acceptably, we use Java. So GUIs and stuff, we're still using Java. But for a lot of the core, under the hood stuff, cluster stuff, we're using Python. 90% of the slides and stuff here are stolen from other people. So I'd like to acknowledge them. All the ones that were spelt correctly were at least stolen from other people. And thank you all for listening.